Calculus is a powerful branch of mathematics. It deals with change. Specifically, it explores rates of change and accumulation. The fundamental theorem of calculus is a cornerstone of this field. It beautifully links two seemingly distinct concepts, differentiation and integration. Differentiation is like finding the speed of a car. Integration, on the other hand, is like finding the distance traveled by that car. The fundamental theorem of calculus acts as a bridge between these two operations. This theorem elegantly reveals that differentiation and integration are inverse processes. Imagine them as two sides of the same coin. This connection allows us to solve complex problems involving areas, volumes, and rates of change with remarkable ease. The fundamental theorem of calculus comprises two parts. Each part offers a unique perspective on this profound connection. Together, they provide a powerful framework for understanding the dynamics of change. Before we dive into the fundamental theorem of calculus, let's understand a crucial concept called the mean value theorem for integrals. This theorem plays a vital role in proving the fundamental theorem. Imagine a curve representing a continuous function over a certain interval. The mean value theorem for integrals states that there exists a point on this curve where the function's value equals its average value over that interval. In simpler terms, if you could somehow smooth out the curve to form a rectangle with the same area, the height of that rectangle would represent the average value of the function. The mean value theorem for integrals guarantees the existence of a point on the original curve that precisely matches this average height. Mathematically, if f(x) is our continuous function over the interval ab, then there exists a point c within this interval such that fc equals 1 divided by b minus a times the integral from a to b of fx dx. This equation tells us that the function's value at the special point c is equal to the definite integral of the function over the interval, ab divided by the length of the interval. Now let's unravel the first part of the fundamental theorem of calculus. This part establishes a profound link between integrals and antiderivatives. Imagine a function fx, defined as the definite integral of another function ft, from a fixed point a to a variable point x. Part 1 of the fundamental theorem states that the derivative of fx is simply fx. In essence, this means that finding the area under the curve of ft from a to x and then taking the derivative of the resulting area function gives us back the original function f(x). It's like taking a step forward and then a step back, returning to our starting point. This relationship is profound because it reveals that differentiation and integration are inverse operations. If we integrate a function and then differentiate the result, we get back the original function. Mathematically, part 1 of the fundamental theorem can be expressed as if fx equals the integral from a to x of eft dt, then f prime of x equals fx. This equation captures the essence of part 1, highlighting the inverse relationship between differentiation and integration. Let's break down part 1 further to solidify our understanding. Picture a car moving along a straight road. The function ft represents the car's velocity at time t. The integral of ft from time a to x gives us the distance traveled by the car during that time interval. Now, the derivative of the distance function gives us back the velocity function. This makes intuitive sense because the rate of change of distance is indeed velocity. Part 1 essentially tells us that if we know the rate at which something is accumulating, like distance traveled, we can find the original function, like velocity, that governs that accumulation. It's like knowing how much water is flowing into a tank at any given moment and using that information to determine the shape of the tank. This part of the fundamental theorem provides a powerful tool for understanding the relationship between a function and its rate of change. It lays the groundwork for the even more practical part 2, which we'll explore next. Section 5, Part 2, the evaluation theorem. The second part of the fundamental theorem of calculus, often referred to as the evaluation theorem, offers a remarkably efficient method for calculating definite integrals. Imagine wanting to find the area under a curve represented by the function f of x between 2 points a and b. Part 2 tells us that if we can find an antiderivative of f of x, denoted by f of x, then the definite integral of f of x from a to b is simply the difference between f of b and f of a. In simpler terms, instead of painstakingly approximating the area using rectangles or other geometric shapes, we can find an antiderivative of the function and evaluate it at the two endpoints of the interval. The difference between these two values gives us the exact area under the curve. This method greatly simplifies the task of calculating definite integrals. It's like having a shortcut that allows us to bypass tedious calculations and arrive at the answer directly. Section 6. Unraveling the evaluation theorem. Let's express part 2 mathematically. If f of x is an antiderivative of f of x, then the definite integral of f of x from a to b is the integral from a to b of f of x dx equals f of b minus f of a. This equation beautifully encapsulates the essence of part 2. It tells us that the definite integral of a function over an interval is simply the difference in the values of its antiderivative at the endpoints of that interval. Part 2 revolutionized the way we calculate areas, volumes, and other quantities represented by definite integrals. It provided a direct link between antiderivatives and definite integrals, making calculus an even more powerful tool for solving real-world problems. Section 7. A parachutist's tale, a real-world application. Let's illustrate the power of the fundamental theorem of calculus with a real-world example. Imagine a parachutist named Julie taking the leap from a plane. As she freefalls, her velocity increases due to gravity. However, air resistance gradually kicks in, opposing her downward motion. We can model Julie's velocity during freefall using a function, let's say v of t, where t represents time. Now, if we want to calculate the distance Julie falls within a specific time interval, we can use the fundamental theorem of calculus. The distance fallen is simply the area under the velocity time curve. Instead of using tedious approximations, we can find an antiderivative of the velocity function, which would give us a distance function. By evaluating this distance function at the beginning and end of the time interval, we can calculate the exact distance Julie falls. Section 8. Freefall and the fundamental theorem. Let's say Julie's velocity during freefall is modeled by the function vt equals 9.8t minus 0.2t squared. This function represents a simplified model where 9.8t represents the acceleration due to gravity, and 0.2t squared represents the opposing force of air resistance. To find the distance Julie falls between, say, t equals 2 seconds and t equals 5 seconds, we can use the evaluation theorem. First, we need to find an antiderivative of vt. An antiderivative of vt is dt equals 4.9t squared minus 0.2 over 3t cubed. Now we can calculate the distance fallen between t equals 2 and t equals 5 seconds using the evaluation theorem. Distance fallen equals d of 5 minus d of 2. By plugging in the values and calculating, we get the exact distance Julie falls during that time interval. The fundamental theorem of calculus makes this calculation straightforward and precise. Section 9. Key concepts, the foundation of understanding. Let's recap the key concepts we've explored. 1. The fundamental theorem of calculus. This theorem bridges the gap between differentiation and integration, demonstrating that they are inverse operations. 2. The mean value theorem for integrals. This theorem guarantees the existence of a point on a curve where the function's value equals its average value over an interval. 3. Part 1 of the fundamental theorem. This part states that the derivative of an integral function gives back the original function, highlighting the inverse relationship between differentiation and integration. 4. Part 2 of the fundamental theorem, also known as the evaluation theorem. This part provides an efficient method for calculating definite integrals by evaluating the antiderivative of a function at the endpoints of an interval. Section 10. Essential equations. Tools for calculation. Here are the key equations we've encountered. 1. The mean value theorem for integrals. F of c equals 1 over b minus a times the integral from a to b of f of x dx. 2. Part 1 of the fundamental theorem. If f of x equals the integral from a to x of f of t dt, then f prime of x equals f of x. 3. Part 2 of the fundamental theorem, also known as the evaluation theorem. The integral from a to b of f of x dx equals f of b minus f of a. These equations serve as powerful tools for solving problems involving rates of change, areas, volumes, and other quantities related to calculus. Section 11. The power of the fundamental theorem. The fundamental theorem of calculus is a cornerstone of calculus. It provides a profound understanding of the relationship between differentiation and integration. This connection allows us to solve a wide range of problems involving motion, areas, volumes, and countless other real-world applications. Whether analyzing the motion of a parachutist, calculating the area under a curve, or solving complex engineering problems, the fundamental theorem of calculus equips us with the tools to understand and model change in a precise and elegant manner. Its elegance lies in its ability to connect seemingly disparate concepts, revealing the underlying unity and beauty of mathematics.